So for this question, we're told that in a pumped storage hydroelectric system, water is stored in a dam of depth 34 meters. The water leaving the upper lake descends a vertical distance of 110 meters and turns the turbine of a generator before exiting into the lower lake. Water flows out of, so part A, water flows out of the upper lake at a rate of 1.2 times 10 to the power of 5 cubic meters per minute, and the density of the water is 1.0 times 10 to the power of 3 kilograms over cubic meters, right? So we're asked to estimate the specific energy of water in this storage system, giving an appropriate unit. Okay. So first thing you have to realize is that some of the water in here, it either travels a distance of 144 meters, or the water here only goes for about 110 meters, right? So you have to take an average. So I'm gonna denote this as h bar equal to 110 plus 144 divided by 2, and that'll give you a value of 127 meters. Now from this equation that I've mentioned, we know that specific energy is basically joules over kilogram. So you have to use this, and it's pretty obvious that the initial mechanical energy, the only initial mechanical energy here is gravitational potential energy. So your specific energy, I'll continue it here, is going to be mg h bar over m. So your m's cancel out. You'll be left with 9.81 times 127. And if I calculate that, it's going to be 1,246 with 4 significant figures. I'm going to put 3 significant figures. So 1.25 times 10 to the power of 3 joules per kilogram. Now everything else here is reported in 2, so I'm going to also mention it with 2 significant figures just in case. Alexa, dismiss. Now continuing from where I left off. So in part 2, we're told to show that the average rate at which the gravitational potential energy of the water decreases is 2.5 gigawatts. The rate at which, so basically joules per second, right? So we got joules per kilogram. So what I would do is I would pay close attention to these units here and see what I can do with them. And also there's per minute here as well, so that's good. All right, so let me rewrite. I'm going to use the unrounded version of my value, so 1.25 times 10 to the power of 3 joules per kilogram. And then if I want to get rid of that kilogram, I would multiply it by 1.0 times 10 to the power of 3, right? 1.0 kilogram per meter cube. And then multiply that by 1.2 times 10 to the power of 5 cubic meter over 1 minute, right? So let's see, your kilogram will cancel out, your cubic meters will cancel out, and you'll be left with joules per minute. So if I calculate this, I will get a value of 1.2, give me a second. Okay, so that's going to be 1.50 times 10 to the power of 11 joules per minute. And now 1 minute is 1 minute is 60 seconds, right? So we can multiply that by 60, divided by 60. So 1.50 times 10 to the power 11 divided by 60. So that'll give you a value of exactly 2.50 gigawatts with 3 significant figures. 2.50 gigawatts. Alright, is that correct? I think. It is indeed correct. Okay, so you can report that into significant figures. Now, the storage system produces 1.8 gigawatts of electrical power. Okay, so efficiency is, this is your output, 1.8 divided by 2.5 times 100, and you will get a value of, let's see, 72%. Not bad. I'm gonna skip. Alright, that's it.